So in this video, we're going to be looking at ozone, chlorofluorocarbons known as CFCs, and how they actually impact the number of molecules of ozone in our stratosphere. Now, ozone is going to be a molecule with a formula of O3, and it's not to be confused with, of course, oxygen, which we use for respiration. We breathe this in. Ozone is a very unstable molecule, and most of our ozone molecules in our actual planet is going to exist in part of the atmosphere known as the stratosphere. Now, ozone is very important because it helps block UV radiation, ionizing ultraviolet radiation, and UV radiation is quite bad because it can actually cause sunburn and skin cancer. Now, when we look at ozone, it actually works by absorbing this UV radiation, and so the UV radiation on the Earth's surface is going to be reduced. That's an actual exam answer that we need to remember when we look at the purpose of ozone. Now, ozone is going to be formed naturally where we end up with a molecule of oxygen. Let's say it's floating about in our stratosphere. We can actually end up with UV radiation breaking this molecule down, breaking the covalent bond down through a process known as homolytic fission, and that is when, of course, our covalent bond breaks and one electron goes to each atom, forming two radical species. Remember what radicals are. They're going to be a species with an unpaired electron, a highly reactive species. Now, these oxygen radicals, they're going to go ahead and react with more molecules of oxygen, and what you actually end up making is of course a molecule of ozone, of O3 itself. So moving on then, we need to be aware of some compounds known as CFCs, and that's going to be short for chlorofluorocarbons, and these are compounds that contain chlorine, fluorine and carbon atoms only, where all of our hydrogens are going to be replaced. Now, let's say if I were to deal with a compound like methane, where I've got, of course, CH4, you can see over here that all of my hydrogen atoms in my CFC molecule, trichlorofluoromethane, all of our hydrogen atoms are going to be replaced with either chlorine or fluorine atoms. That's what makes a CFC. Now, CFCs, they were used quite a lot in the past in aerosol cans, dry cleaning, air conditioning and the coolant gas in fridges, and this was because they were stable, they were volatile, non-flammable, and they were non-toxic as well. But the thing is, right, we actually stopped using these quite a while ago, mainly because they were destroying the ozone layer. Now, of course, they weren't actually toxic. We didn't actually notice anything when we first started using them, when we got them in contact with our skin, in the air that we breathe, because there's actually nothing wrong with them apart from the fact that they're destroying the actual ozone layer. Now, the main problem is with these CFCs is that under the presence of UV, they actually undergo homolytic fission, and we end up producing chlorine radicals. Now, these chlorine radicals are going to be quite bad because they actually catalyze a breakdown of ozone. Now, looking at this example over here, you can see I've got an example of a CFC. It's going to be dichloro, difluoro, and it's going to be methane. We can see that under the presence of UV, we can actually end up with homolytic fission taking place, where we end up with our carbon chlorine bond actually breaking and one electron going to each atom, forming radicals. That's what you can see that's happened over here, and we've actually ended up with a chlorine radical and the remainder of that CFC structure being a radical as well. Now, the important one is a chlorine radical because that's going to go ahead and react with ozone. It ends up stripping off an oxygen to make a chlorate radical and then a molecule of oxygen. After that, that chlorate radical will continue to react further on, where it will react with another oxygen atom and it will form a molecule of oxygen again, and then the chlorine radical is going to be regenerated. Now, we know, of course, this reaction, it hasn't terminated, and it won't really terminate up until about 10,000 molecules of ozone has been destroyed, and so this reaction will actually have chlorine as a radical. That's going to be the catalyst itself. So again, this process repeats itself about 10,000 times, and then, of course, it reaches termination where it bumps into something else like another chlorine radical. Now, this is a problem because, of course, we know ozone, it protects us from UV, it stops UV from reaching the Earth's surface, and this is a problem that the UK has actually addressed by banning the use of CFCs across industry. So yeah, what's the actual overall process that's happening? What's an overall equation that we can make from this? Well, let's say if I were to combine both of these two equations here together, and I can actually end up with the reactants on one side, products on the other. If I were to look at my catalyst, whatever is on both sides, I can actually cancel. If I were to look at my intermediate, this chlorate over here, this chlorate over there, they can cancel, and what I'm left with is oxygen reacting with ozone, forming two lots of oxygen O2 molecules itself. And that's the equation, the overall equation over here, that you need to be able to remember as well. And just remember that chlorine radical, that's going to be acting as a homogeneous catalyst in this case. So moving on then, looking at another example of a radical that's going to be damaging our ozone layer, nitrogen monoxide radicals or nitrogen oxides, they're going to be formed from thunderstorms, car engines, and then aircraft engines as well. When we look at car and aircraft engines, we actually end up with large amounts of heat generated from these, and what actually happens is atmospheric nitrogen, atmospheric oxygen, they're going to fuse together, making nitrogen oxides. Now this is a very similar reaction to our chlorine radicals catalyzing the decomposition of ozone, where we take our nitrogen monoxide radical, that reacts with ozone, we end up forming oxygen, and again that nitrogen monoxide is going to strip off one of these oxygen atoms, making nitrogen dioxide. Our intermediate nitrogen dioxide will react with another oxygen atom, and we end up forming oxygen gas and nitrogen monoxide again. And you can see over here that nitrogen monoxide is going to recatalyze the reaction again. It's going to find another molecule of ozone, and it's going to do this many times again. Now if I were to look at forming an overall equation from this again, you can see over here I've got my reactants on my left hand side over here, and then my products on the right hand side. Combining these two equations together, I've got nitrogen monoxide, cancels with that over here. I've got nitrogen dioxide, cancels with this over here. So overall I've got ozone reacting with oxygen, forming 2 molecules of oxygen gas. And so my overall equation is going to be ozone reacts with oxygen, same as before, to form 2 molecules of oxygen gas. But in this case, rather than having chlorine radicals as our catalyst, we've actually got nitrogen monoxide as being our homogeneous catalyst itself as well. So moving on then, I've got a task for you to try. Feel free to pause the video and have a go at the following task. Resume once you're ready to go over the answers. So looking at this question then, we've got Freon 13. It's a CFC with a molecular formula of CClF3. In the upper atmosphere, the presence of Freon 13 can lead to ozone depletion. Explain with the aid of equations how Freon 13 can lead to this ozone depletion. We need to use dots to show the position of unpaired electrons as well. Now there's a couple of steps that's going to happen here. We've got initiation, our 2 propagation steps, and then of course our final equation as well. Now the first thing that's going to happen is we're going to take this actual CFC itself, this specific CFC, which is going to be CO, and then it's going to be F3, and that's going to undergo homolytic fission under the presence of UV, and we end up producing CF3 as a radical. In this case, the radical is going to go on the carbon, so I'm going to end up with a radical next to it over here, big fat dot, and then I'm going to end up with my chlorine radical, the most important radical here. Now we're going to end up with that chlorine radical that's going to go ahead and it's going to react with a molecule of ozone, and what we actually do is we strip off an atom of oxygen, so we end up with a ClO radical, and then we also end up with our oxygen gas being produced. Now that chlorate radical is going to go ahead and it's going to react with another atom of oxygen, not going to be a molecule of ozone in this case, although in the AQA spec they actually put O3, in OCR we actually put O, and what we actually generate is a molecule of oxygen again, and then we also end up reforming our catalyst itself, which is going to be our chlorine radical. Now with these 2 propagation steps, I need to produce an overall equation over here. How am I going to go about doing that? Well, I'm going to combine both of these 2 equations together, take my reactants on the left, products on the right. I cancel what's the same on either side. So I've got chlorine radical there with chlorine radical there. I've got chlorate radical here with a chlorate radical here. So all I'm left with is ozone reacting with oxygen, gives me 2 molecules of oxygen gas itself. So I rewrite that out. I've got ozone, that's going to react with oxygen, and I end up producing 2 molecules of oxygen gas itself. Again, you get 1 mark for each of these answers over here. So yeah, moving on, I've got another task for you to try. Feel free to pause the video and have a go at the following 2 multiple choice questions. So yeah, in the first instance, you're dealing with CFC, that's going to be CCl2F2. This causes the breakdown of ozone in the upper atmosphere. Which initiation step could occur with UV radiation to catalyze the breakdown? Now we already know that we're dealing with this CFC itself, and I always like to write out an equation where I've got CCl2F2, that's going to break down under the conditions of UV, and we end up producing CCl, and then it's going to be F2 as a radical. Again, big fat dot goes over here, and then I end up with, of course, a chlorine radical as well. Now I need to look for the equation that matches this one, or that actually produces a chlorine radical to narrow it down. Can't be A because that produces a carbon radical, that's a bit weird. Can't be B because that produces a fluorine radical. Can't be D, that produces a chlorine molecule as a radical, which is quite strange. The only answer, the actual equation that matches matches exactly is going to be C. So we know the correct answer is going to be C. Look at the next one. The breakdown of ozone is catalyzed by nitrogen monoxide radicals. Which equation is a propagation step in the mechanism for this process? Now, if I were to write an equation for this, I've got nitrogen monoxide. That's going to react with, of course, ozone. We end up producing nitrogen, and then it's going to be dioxide plus oxygen gas. This intermediate that's going to be produced, that's going to, of course, react with an atom of oxygen, and we also end up producing, in this case, oxygen gas, and then we reproduce our catalyst over here. Now, either one of these two equations, whichever matches up with A, B, C, or D, that's going to be our answer. So we look at the first one, can't be the answer because we're producing ozone. Look at B, that's going to produce NO2, and O, that's going to be wrong because, of course, we know them two actually react together, so the equation's in the wrong direction. Look at C, that's not actually going to be the answer as well because we actually take ozone here and react it with N, and N is not going to be our radical. It's going to be D in this case because it matches up with our equation that we've got over here itself. So in that case, the answer is just going to be D, and there's those two done. So moving on then, we need to be aware of some alternatives when it comes to our CFCs, because CFCs, they're going to be pretty much illegal everywhere. We can't really use them in the UK. An alternative is going to be a HCFC, and that's when we have, of course, a hydrochlorofluorocarbon. In this case, we've got a hydrogen in there, and what it means is that this molecule will actually break down a lot quicker compared to our CFCs. It will actually break down in 10 to 20 years compared to the original 90 years of our CFCs. Another alternative is going to be HFCs, where we don't actually have any chlorine in there whatsoever, and we actually have in there just hydrogen, fluorine, and carbon, and these aren't actually going to affect our ozone layer. The only problem with both of these is that they're actually going to be greenhouse gases, and they contribute towards global warming. Now, some other alternatives for CFCs that we can actually get is, of course, our mechanical systems like pump action sprays, where we can actually use changes in pressure to squirt something onto a surface. We can also use different propellant gases, something inert like nitrogen. When we deal with fridges and freezers, we no longer actually use CFCs, but instead we prefer to use something like ammonia, or even something like cyclopentane, which looks something like this as a coolant gas. Now, CFCs were also used a long time ago when it came to, of course, packaging. You've probably come across it at the takeaway before, where you end up with that spongy plastic packaging. CFCs were used to make expanded polymers, but now we use something like carbon dioxide. And to be honest, we don't really use plastic anymore. Most places they actually are switching to, of course, paper to comply with the changes in the government's initiatives on recyclable waste. That's pretty much all of our alternatives that we can come across when it comes to CFCs.